Hey guys, yeah, we're back again in the studio. Cool. So yes, so today we're gonna do a comparison between SymPy in Python and the Julia language. Okay. So it's just a linear algebra comparison between the two languages and stuff. Okay, cool. So on a side note, guys, I'd really appreciate it if you do subscribe to my channel. So if you love what you see, please do subscribe and please do share the videos with your friends. So share them on Twitter, Facebook, Instagram, whatever it is. Yeah, please do share it. Okay, cool. So let's get started. So from then SymPy import star init printing. There we are. And then x equals to symbols. Okay, so Julia, right? So we loaded Julia there, right? So I got using linear algebra, right? Linear algebra X as well. Algebra X roots polynomials. Right, so we loaded our packages. Okay, cool. So I've got a matrix M, right? And then so 1 0 0, right? And then minus 1, then 2, then 2, and then 4 3, and then 5. Similar to the way you put the matrix, enter a matrix in Julia, it's just the same as MATLAB. Okay, cool. So we got a matrix M, right? And then in SymPy, a bit long-winded, so my matrix, and then so 1, then 0, and then 0, right? Minus 1, then 2, 2, okay, and then 4 3 5. So 4, and then 3, and then 5. Right, so that's M. So there's a matrix, right? So what we're gonna do now is find the determinant. So det, then M, right? Now, type in a little comment. So a matrix is invertible if and only if det is not 0, right? So we got our determinant there. That's 4. So come and copy that, right? So here's det, and then M, and then command V, right? So we got 4, right? You can also do it this way. So M dot det, there we go, 4, then det, then X M, right? So that uses this this module, okay, the X module, okay, and this one is just that one, okay, right? And since we got a determinant that's not 0, so we've got an inverse. So inv M, there we are, and then M dot inv. So there we are. I would prefer it this way, decimals instead of fractions. I prefer that, Okay, and then since we've done our inverse, now we're gonna find the characteristic polynomial. So z equals to car poly underscore poly, and then m belong, takes a bit of time with that one, right? And then z as well is equal to m dot car poly. So z, there we are. So x cubed, sorry, yeah, lambda cubed, 8 lambda squared, 11 lambda minus 4. Yeah, it's just the same much. Should have used x there. Okay, let me do it this way. So command copy, paste that in there. Right. So z. Yeah, so there we are. So x cubed, x squared, and stuff and so forth. So same thing here, right? Right. So root m sorry, so root z, my bad. There we are. So these are actually the roots to the polynomial z. So sorry, I made a mistake there, sorry. Okay, cool. And then cracking on. So type in eigenvalues. So eigenvals. It's the same as the roots, right? And then so m dot eigenvalues. Right. So there we are. I prefer that. I prefer Julia in this instance, right? Things are a little bit neater, right? And then the eigenvectors. So m dot eigenvects. Right, great, right? And then eigenvex m. There we are. You see, a little bit tidier, I mean, all the same, but I would prefer Julia. It seems to be a lot more neater and stuff, that sort of thing. And a bit more efficient as well, a little faster. Okay, so that's eigenvex. Now the trace, so tr, then m, so just the sum of the diagonal, and then here it's just trace m, right? And then reduce row echelon form, so m dot rref. There we are, and then rrefx. Right. Okay, so it's just an identity matrix, right? And then the transpose. So transpose m, right? And then transpose, right? So the diagonals just stay the same anyway. And the trace as well, like I said, is the sum of the diagonal entries. So 5 plus 2, 7 plus 1, 8. Okay, and then I'm going to exponentiate. So exp m squared. Now look at this. 108 lines. Great. So there we are. So start off with e, so the exponential function and so forth, right? Now look at this. Exp m squared. Right, so the exponential function 2.71828, 0, 0, and so forth. A lot neater, right? A lot better, as compared to that, Yes, numerically, I mean, it's the same, but this is a lot better and stuff in terms of like efficiency and stuff. Yeah. Okay, cool. So yeah, it was just a vid doing a comparison between the two languages. Personally, I prefer using Julia because it looks very neater and stuff, and very fast in terms of rendering stuff. Yes, I know the polynomial part, the characteristic polynomial is a bit slow, but anyway, you can live with that. Okay, cool. So yeah, like I said, guys, if you love what you see, please do subscribe and please do share the videos with your friends. And cool. So have a good one. Cheers. Bye bye.